Hello, everybody. Welcome to SRA 365. I'm, of course, Professor S, and this is this week's lecture. So before we get into new stuff, one of the things that I want to talk about is what we've done so far. So far what we've done is we've predicted responses with predictors, and those responses are they're continuous values, right? They're numerical values, and we come up with a best fit line to kind of predict those values in between. But what if, instead of a response being a continuous value, we want it to be more of a categorical value where it's either is something or it's not, like that sort of identity sort of thing. And that's where we enter in a new type of regression, which is our topic for this week, which is binomial logistic regression, which is often commonly referred to as logistic regression. So anyways, the way that this works is this is kind of the representation, or I guess I should say this is the kind of representation of it. The idea is that the model helps make predictions of the response based upon the predictors, just like before, except this one, it's either, like I said, it's either is something or it's not, right? And so it's either, if it is, it's a 1, if it's not, it's a 0. And so here is our actual model that we will be using. It's up above here. It's kind of confusing. I mean, it has kind of that linear sort of aspect in a tiny part of it, but it's kind of a little bit more complicated. And it's interesting how determining whether something is something or it's not turns into a little bit more complicated thing. But one of the things that I want to kind of point out is, like, in our model, it's P of Y, right? It's the probability of something happening. That's what our model is saying. It's not, before we're saying, all right, it is going to be this or it's not. We're thinking about how likely something is. Okay, so kind of, if you kind of look at where these values are, so notice that the green dots over here, these are the different values. So the ones that, so as still the predictor is the X values, but the Y values, that's the responses. Okay, so notice it is either is something, it's a 1, or it's not, and it's a 0. And we're trying to fit this S-shaped curve to kind of figure out the probability that something's happening, right? So kind of think about it this way. These areas, right, this area right here, this is probably going to happen, or probably not going to happen, excuse me, because it's 0. Whereas the area over here and beyond would be probably going to happen. Whereas the area right here, it's a kind of, I don't know, it could be either one. And so that's what our model is saying. So our model is coming up not with the value, whether it is or it's not, it's coming up with that it's determining the probability that it is. So, because also notice that there's this whole area in between, like I just said, where it could be either. So notice as it gets more to the right of that, it's more likely, and as it gets further to the left of it, it's less likely. Okay? And so that's kind of what we're going to do. So before we get into too much of it, let's just kind of see what this looks like in R. So what I have open is the script that came with the text, and I kind of want to walk through it, talk about kind of different ways to approach it, kind of what's going on, that sort of thing. So first of all, for me, when I downloaded the file, it doesn't work, right? It doesn't import the data, so see, doesn't like it. The reason being is that if you look at the file, this says cyber attack v4, and the file is cyber attack v4-1. So we need to make sure we include that -1 so it matches exactly with what it says that the file name is. So when I run it, boom, it likes it, right? So now the thing is, it's like the next thing that I want to try to address is line 7, where we have library car. We don't really need it. I don't know why this was included, but the function that we're going to be using for making our models doesn't need the library, doesn't need the car package to do this. So I don't know why we're including it. Maybe it once did, but it doesn't anymore. So anyways, to create the model, we're going to store it as this, very similar to how we did the simple regression models. But notice that our model here is GLM instead of just LM. Okay, so it's important that we use GLM for this binomial log regression, right? Also, another thing is like, since this is a binomial log regression, we need to say at the end, or include in somewhere here, family equals binomial, to indicate that it is a log regression. Other than that, everything should look pretty much the same, where we have formula with the predictor, and then we're saying what the data frame is that we're referring to. Easy enough. So that when we run it, it should work, but it doesn't. Because the thing is it's not because of the package, it's because of the value of y. Notice that our y value, our response, is fin loss, and that it's either no, or there's also yes is also a possibility. You can't see it, but it is. So what we have to do is this line right here, where we convert it to a factor, because right now it's just a bunch of strings. So when we convert it to a factor, it's either no or yes, as it says here. So notice it says 2 levels, no or yes. And remember, it was before it's a bunch of no's, and now it's a bunch of ones, right? No's are ones, yeses are 2s. Where did they get that distinction that no should be that? Remember, no starts with an N, yes starts with a Y, no comes before N comes before Y in the alphabet, so that's how that works. If we want to change those levels so that yes is the base and no is not the base, then there's an easier way that we could do it than we've approached it so far, but we'll get into that in a little bit. I want to kind of get this so far. So far what we're going to do is that when we run this, we're going to create our model, and it's going to say whether it is a financial loss or it's not, right? So if it is or it's not. So if it is, it's going to be a 1, and if it's not, it's going to be a 0. Kind of similar to what it is now, but we have 1s and 2s, so it kind of just shifts it down to 2s and 1s. Okay, so to kind of see what this data looks like, we'll use summary again of our model, and there it is. It works great. Still haven't loaded that car package, and everybody's happy about it. So notice that it all kind of looks the same. This stuff is a little different, and we'll use the null deviance and the residual deviance in a little bit. But first, let's kind of think about these values right here. So remember that crazy expression that I had on the slide before that said how we come up with that prediction? That's the values that we use for those coefficients, whether it's the intercept or the coefficient for our predictor value, that's all right here. And then the p-values for the level of significance are right here. So right now, notice that the response time is significantly influencing the data. So it's a significant predictor so far as we can tell. Whether it's saying that as response time increases, it either becomes more likely or less likely. But it's kind of hard to see from that, so we kind of need to know something to kind of help indicate, does it become more likely as the response time increases, or does it become less likely? And that's where the odd ratio comes in. But before we work on calculating that, let's kind of just use this as a prediction. So right now what I can do is I can come up with a prediction when the response time is 1. Okay, so when I have the response time as 1, notice that here's the intercept. There's this the coefficient for response time. When I run it, not super likely. When I run it for 2, also not likely. But since we're going from a 1 to the next highest 1, 2, that helps us come up with the odd ratio. So what I can do is I can run these lines right here. Actually all these lines right here, and it will come up with our odds ratio. So I'll run it, and then the value of OR is our odds ratio is 1.006521. And we're going to interpret what that means, but really as far as we're concerned, this is 1. Okay. Another way that we can kind of find this odds ratio out, and this is going to be way easier. That's why I didn't focus on this, because I don't expect you guys to calculate it this way. It's just putting that coefficient that we had up here. Let's see, where is it? Right here. We're putting this coefficient in for the e to the whatever, right? This is the whatever part. So notice when I do that, that's what this is finding here. E like the Euler's number. When we put this to as the power, notice it gives us 2 values. This is it. because what it did was it took both intercepts and it put it to the power of e, right? So e to both of those coefficients gives us these two numbers. This is for the intercept. This is for the response time coefficient. We want it for the response time coefficient because that's our predictor coefficient. The predictor coefficient is the one we want. Notice that it is 1.065, pretty close to the number that we came up with right here. Let me just run it real quick. There it is. So notice that they're pretty much the same value. This is just a way easier way to come up with it. Another way that we could kind of come up with it, maybe kind of an easier way to see it, is like, remember this is our coefficient right here. So if I just copy this and say exp and I put that value in, notice that when I run it, it pretty much comes up with the same value. It's rounded a little bit, so it's going to look a little different maybe, but the idea is it's like, well, it is rounded because the idea is that the coefficient that was used here is a rounded, this is a rounded version of the coefficient that was used here. When it's displaying the summary, it rounds it a little bit. But those are two different ways that we could find it. Let's kind of go into the slides again and talk about what the odds ratio is. Okay. The odds ratio, we didn't talk about what too much of it is, but it kind of helps us do a couple of things. So first of all, notice the two different odds ratios that we have here. The one on the left, that is saying that the outcome decreases as the predictor increases. So notice as the values of x increase, there's more dots that keep on going down. So that's where the odds outcome decreases. And then the odds of the outcome increases, that's where it becomes more likely as the predictor increases that the response is going to be more likely to be true, or is whatever we're saying our one is. Okay. Now, what the odds ratio is talking about the effect size. And there's like kind of a couple different ways that you can calculate it. The book or the text kind of goes through like the basics of what's going on, but really the way that you calculate it is, as I showed you, is that we take that coefficient, we put it to the power of e, right? That Euler's number, right? And so that value of the odds ratio kind of tells us whether the outcome is increasing or decreasing, or if it stays the same. Now, really, when we're trying to determine if it is the relationships, we want it to kind of be in either direction. We want it to be either the odds ratio to be definitely greater than 1 or definitely less than 1, right? And so otherwise, there's no relationship or there's something wrong with our data. The other thing is that the odds ratio kind of helps us determine the effect size. So it's like, how much is increase the likelihood, or how much does it decrease in likelihood that something is going to happen based upon this predictor? Okay. The other thing that we need to talk about that we had that was very helpful for the simple regression was coming up with that, knowing if it was best fit, right? We used R squared. And remember, the R squared was kind of looking at the residuals of the data. Residuals are kind of like, remember, residuals are where we're comparing the predicted values with the actual values. And that's kind of not something that we can do with our model, because remember, our model is predicting the probability. It's not saying that it is or it's not. It's saying how likely something is going to happen. So we don't really have residuals because nothing actually fits on the line the same, or fits our model the same way that it does for a simple regression model. So we got to kind of use a different value. And there's other pseudo R squareds, but the one that we're going to be using is the McFadden R squared. So it's technically not the same value, but we're going to kind of use it in the same way, where we're going to kind of use it to help gauge the fit of our model to the data, right? How well does this model fit with the data? And so the way that we do this is we do 1 minus the residual deviance divided by the null deviance. Okay, and the values that we're looking for is above 0.2. That's an arbitrary value, but we're going to just say if it's greater than that, then we're convinced that it's a good fit. So let's go into R to kind of see how we calculate this and see if our data actually does that. So what I have done is we're back. This is the summary of the data so far. And so what we're going to be using, but the idea is like what we're doing is we're coming up with that McFadden R squared. And the idea is that it is 1 minus, and we use this, the summary to get that data. We come up with the residual data, and so I could just copy it. And actually, we want this in parentheses. There, I'll paste it. And then divided by the null deviance. And then when we run this line, we get 0.51777656, right? So remember, our value that we want is greater than 0.2, so this is considered a pretty good fit, okay? It's not saying anything about the relationship, it's just saying how our model fits our data, right? The odds ratio helps give us an idea for the effect size, the direction, and that sort of thing. But one of the last things I want to kind of point out is the leveling. So remember with the factoring, this is either a 1 or a 2, right? This is, if it's a no, it's a 1, and if it's a yes, it's a 2. So which kind of, remember our dummy variable is going to be yes. And so if it's a yes, it's a 1, and if it's a no, it's a 0. So what we're kind of seeing is like with this data is that with the base being no, we're finding out the probability that it is yes. That's the probability that there's a financial loss. Okay, but what if we want to know the probability that there isn't a financial loss? What if we want to know that the probability of fin loss is no? And so then the idea is like we have to rechange the way we level. So first of all, we're going to use this function right here, relevel. Notice that we have our data frame here, our variable. So it's like the first thing is talking about the variable that we are changing, and we're changing it. We're applying these changes to this variable right here, and we're going to use the relevel, and then we're changing it to, let's just change it to no real quick. So if we run with no, watch what happens to this. So run, nothing changes, right? It was 1 before, and now it is still 1 because no comes before yes alphabetically. So that's why it does that. But if we wanted to change it so that it is yes, then we change this. And notice that it goes yes, no. Before it was no, yes, and it's a bunch of 2s because the 2 is the no. The yeses are going to be 1s. Okay, so that's how we relevel, and we can come up with a completely different model when we run this here that will come up with a probability that there is not a financial loss. So notice different values right here. Okay, if you look back. Anyways, let's go back to the slide where I'll finish things up. Something that I want to emphasize for question 1 and question 2 is that you need to change the response variable to a factor and be very mindful of that base. We talked about this already, but just keep that in mind when you're doing these two problems. What's the base? And you might need to change it. Okay, that's my big hint. Anyways, good luck on the lab this week, and I will see you all later. Bye. Hey everyone, I hope you enjoyed that video. If you did, please press the like button below. It lets me know I'm doing something right. If you have any questions about any of the content, please send a message in Canvas to both me and the rest of the teaching team, and we'll get back to you as soon as possible. If you have any suggestions for how I can make these videos better, please leave in the comments below. Don't forget to roundhouse kick the subscribe button and ring the bell to get notified for when I post the next video. Anyways, I think that's good for this video. I'll see you all later. Bye.